In our first example, we consider whether it's worthwhile to purchase a rail card. In the UK, anyone under 26 can buy a card for £24.
That will get you 1/3 of each journey you make. In other countries, the rail card will cost a different amount and you'll get a bigger or smaller discount. But let's concentrate on the UK. Is it worthwhile? How many journeys do you have to make before it makes sense to invest in the rail card?
Alex Sellner is an Austrian student studying in the UK. At home, a rail card gives such benefits that it's almost always worth buying one, even for one journey. In the UK, the relatively high cost of train travel and the rail card means that the calculation needs more thought. So Alex, you're not an English student, so what are you doing here?
I'm an Erasmus student, studying for 1 year in Great Britain.
And enjoying it?
Yeah, enjoy it a lot, yeah.
And
met a lot of new people by now and from other cultures and yeah.
And do you get to travel around much and see other parts of the UK?
Yes, of course. I got some friends which I visit quite a lot. There's one friend I've been visiting 2 times now. I want to go. I'll probably visit him some more times.
And what's the cheapest way of doing it?
Yeah, actually, I'm going by train everywhere, but I'm not sure. Either buying a card to get a discount or just buying a new ticket each time I go. Not sure about that.
So you've got a decision to make to work out what's the cheapest way of doing it?
Yes, of course. Hello, can you give me some information on the young person's railway card? How much is it?
The card costs £24 and saves 1/3 of the cost of a journey. He wishes to visit a friend sometimes, and each return trip costs £12 without a card. So how many journeys are needed to justify the outlay on the purchase of the card? For different countries, the cost of a rail card and the size of the discount will vary. But it's not difficult to work out for any particular country whether the card is worthwhile, and we can do it simply by understanding linear equations. We represent the problem as one having 3 linear equations. The first one is the relationship between the number of journeys taken and the cost of the journeys if there's no card. We can call that P times Q. Then the second relationship is between the number of journeys taken and the cost of the journeys when there is a card. We could call that A times P times Q, where A is the proportionate reduction in price, so that A will be somewhere greater than 0 but less than 1. It may well vary between countries. But then the third relationship we need to look at is the one between the number of journeys taken and the cost of acquiring the card itself. We could call that FC for fixed cost, because it is a fixed cost. The cost of acquiring the card is independent of the number of journeys taken. So we've got 3 linear equations to work with here, and we can solve if we know the cost of the card and the price of the journeys, and we can do that by combining our second and third equation together. That is to say, we're adding the fixed and the variable cost together to get the total cost of taking journeys if we have a card, which we can compare with the total cost of taking journeys without a card. So we could express it like this. We're looking for the minimum number of journeys needed to break even, such that we're indifferent whether or not we acquire a card or simply do without. Let's assume that the cost of the rail card is £24. And in the UK, if you have a card, you can get a discount of a third. Now clearly, the break-even point is affected by the price of the journeys, as well as the cost of acquiring the card. We'll assume that it's a £12 day return that we're interested in if we can't get a discount. So we're looking for the break-even point, so we can say that B, the break-even point, is P times Q, that's the cost when we don't have a card, minus, and this is where we sum the fixed and the variable costs together to get the cost if we do have a card, minus FC plus A times PQ. Now we're looking for the break-even point, so we set B equal to 0. So that gives us that 0 equals P times Q minus FC plus A P times Q. That is to say 0 equals, now the assumed price of the journey without a card is £12, so 0 equals 12Q minus 24, because that's the cost of getting the card, plus 8Q. 8, because if we have a card, we can get a third off that £12 price. So 0 equals 4Q minus 24, Q equals 6. So if our student takes 6 journeys a year, it's a matter of indifference whether the card is acquired or not. If more journeys are taken, it makes sense to purchase the card. We might want to see this diagrammatically, and it's not difficult to show that because we can plot all 3 of these equations from any 2 pairs of coordinates, because they're all equations of straight lines. So on our diagram we've plotted first P times Q, and then secondly A PQ, and notice that this line rises more slowly because each journey costs less. And then thirdly we've plotted FC, and notice it's a fixed cost, so costs don't rise as we take more journeys. But even if we take no journeys at all, we've still got the £24 cost to meet. Finally, on the diagram, we've added the fixed and the variable costs together to get the total cost if we have a rail card. Now look at the diagram, and at what point does FC plus APQ cross PQ? And the answer, of course, is 6 journeys at a cost of £72. That's the break-even point that we found diagrammatically. Now, many problems can be seen as the solution of simultaneous equations. It doesn't even matter if there's more than 2 equations, provided that there are no more unknowns than there are equations.